Hello everybody. This is the second of two videos talking about betweenness centrality for nodes in a network. Let's do a small recap. We were considering a small network of 5 students who are passing notes to one another. The lines indicate a nice easy note passing step in between two students. We wanted to figure out which one of these students is at the highest risk of being caught. To do this, we started developing the ideas behind this notion of betweenness centrality. In our next step, we listed out all possible pairs of students that might want to communicate. For each pair of students, we kept track of the shortest paths that a note could take inside of the network, and we kept track of how many options for shortest paths there were for each pair of students. After completing that step, we end up with this long form table. After this, we want to start erasing any node that's at the start or the end of one of the shortest paths in our columns. The purpose of this is to focus on the between nodes, or the nodes that are going to appear in the middle of a shortest path. Here's what we have after erasing our starting and ending nodes. And we notice that some rows don't have any content at all. So we can actually make this table a lot shorter, a lot more concise, and we end up with what we called a reduced table. In our first video, we used this reduced table to distinguish between two types of nodes. The nodes that survive this calling process, they still appear in this shortest path column. Now for our reduced table, these are going to have non-zero betweenness centrality. The ones that don't appear anymore, and we've highlighted these in gray to the left, these are going to have 0 betweenness centrality. I promised you an answer to an important question. How do we compare between nodes that have a non-zero betweenness centrality? So for example, if we're thinking of this as students passing notes in our class, we know that A, D, and B are all at a higher risk than C and E. However, who's at the highest risk? How do we compare these nodes who have non-zero betweenness centrality? In order to accomplish this, we need the full definition of betweenness centrality. Now, before you run and hide, give me a second to walk you through this jumble of notation and what it means. You'll be surprised at how straightforward it is to compute this metric. Here's the idea. We're going to use our reduced table to compute betweenness centrality. Each one of the symbols over here is going to refer to something that we're going to do with the table. To get started, this big summation symbol with s's not equaling v's not equaling t's is essentially telling us to consider each row in the reduced table. For each row, we're going to do a small little computation. First, for a given row, we're going to count how many shortest paths actually contain our node of interest. This is what this sigma st of v in blue is representing. Count how many shortest paths contain the particular node you're focusing on. We're going to take that count and we're going to divide it by the total number of shortest paths for that row. You'll notice that as we built our reduced table, we kept track of, row by row, the total number of shortest paths. So this division is essentially going to just look into a separate column of our reduced table. The last thing we do, now that we have computations for each row inside of our reduced table, we're going to add up all of those computations together. It's easier to understand this when you go through an example. Let's try to compute the betweenness centrality for the node A. As we're doing this, it'll help to highlight A inside of our reduced table. Now we're just going to follow the recipe given by our formula. So we start for each row in the reduced table doing a small computation. Here's my first one, the AE row. How many shortest paths in this row contain A? 0. How many total shortest paths are there? 1. Here we're pulling this from our next column. So this small computation associated to that row for the node A is just going to be 0. In our next row, for the BC row, we count how many shortest paths contain A. We see that A only appears once, so we have 1. There are 2 shortest paths, so our computation for this row is going to be 0.5. In our third row, A appears once out of 2 possible shortest paths. Our computation's 0.5. And then finally, A doesn't appear at all, and there's 1 shortest path from D to E, so we end up with 0. Now there's one step that we haven't done yet. This is our final line of our recipe. We have to add all of these small computations together, and this gives us our betweenness centrality. So in this way, we've used our reduced table to compute small computations for each possible row, added those up, and that ends up equaling our betweenness centrality. So the betweenness centrality in this case of A is equal to 1. Following this, we can do similar computations for both B and D. I think it's helpful for you to try this on your own. Go through line by line, do the individual computations for the node B and for the node D, and see if you end up with the same answers that I have. Here are your individual computations written out, and we remember that the betweenness centrality for a particular node ends up being the summation of these values. So the betweenness centrality of B is going to be 3, and the betweenness centrality of D is going to be 1. Let's create our report. Remember, for centralities, each node has its own measurement. So what we need is a table that lists every node in our network, and then to the right, we're going to list the betweenness centrality for that node. In our initial investigation, we saw that C and E have 0 betweenness centrality. We then explored the definition of betweenness centrality so that we could measure the ones with non-zero. We used our reduced table and our recipe for computing betweenness centrality to figure out that A has a betweenness centrality of 1, B has a betweenness centrality of 3, and D has a betweenness centrality of 1. This completes our report on the betweenness centralities of our network. So let's think back to our original application. Here we have a classroom, and we have 5 students passing notes, and the way that they pass notes is represented by this network. We wanted to know who is the student that's most likely to get caught, and we were using betweenness centrality to measure the risk of a student being caught. So, if from our previous computations, we label the betweenness centralities for each one of the students, betweenness centrality measured for these note-taking paths, then we can highlight the one that has the highest betweenness centrality and hence the highest risk of being caught inside of this classroom. In a more general statement, you want to think about betweenness centrality as being a comparative measure, comparing nodes inside of a network. It really just looks at how often a particular node appears in the middle of a shortest path between 2 other nodes. Now, if we apply this to a particular context, betweenness centrality takes on meaning. In our note-taking example, it's these nodes with the highest betweenness centrality that essentially identify students who are passing the largest volume of notes. Not only are they passing notes for themselves, but they're also passing notes for their peers. This increased volume of note passing put these students with the high betweenness centrality at the biggest risk of getting caught. Let's consider one more setting. Remember our telephone tree. In this case, we had one person calling 2 others, who calls 2 others, who calls 2 others, etc. You can do the computations, but convince yourself that these nodes down here at the bottom, these will have a betweenness centrality of 0. They're never going to appear in the middle of a shortest path between 2 other nodes. However, if we consider a node like, say, this one, this is going to have a non-zero betweenness centrality. One way of thinking about betweenness centrality in the case of a telephone tree is as a measure of importance for information flow. Think about if we were to remove one of these leaves, one of these nodes at the bottom of the telephone tree, it wouldn't affect the information to the rest of the network. However, if I remove this node, which would have a much higher betweenness centrality, then any information that comes along this line wouldn't get passed forward to the ones following it. So in that way, betweenness centrality, in a sense, gives us a comparative measure of how important a particular node is for the information flow inside of a telephone tree. As you do more examples, consider more networks, and work more with betweenness centrality, you'll start to develop an intuition for it. Let's do just 2 more examples to start getting you headed in that direction. Here we have our familiar complete network. In this case, each node is connected to every other node by a direct edge. If we think about betweenness centrality, we have to think about, is there any node inside of this network that's going to appear in the middle of a shortest path between two nodes? Well, it's impossible for that to happen because if you take any pair of nodes, there's a line that connects them directly. So you should never pass through another node if you're trying to get there in the quickest possible fashion. So in terms of the shortest paths for this network, they're always going to be direct edges, so there won't be any between nodes. So we can summarize this by saying our betweenness centrality is 0 for all of the nodes in a complete network. So here's one for you to practice on your own. Here's a very simple bucket brigade example. We have 5 different nodes, and they're set up as follows for our network. Ask yourself these 2 questions and see if you can answer them without going through the full computations. Which node or nodes will have 0 betweenness centrality? Of the ones remaining, which will have the highest betweenness centrality? This is a great exercise. And see, when you're done, if you can kind of explain your answer why. Justify your answers to these questions. After that, I recommend actually doing out your reduced table and computing the betweenness centralities for all the nodes in this basic bucket brigade example and checking your answers. Were you right?